In the previous lecture, we have studied about Lorentz force. We have studied basics of Lorentz force. In the present lecture, we will discuss further the significance of Lorentz force and the possible applications of Lorentz force. We should take the basic expression as a prerequisite for this lecture. In this lecture, first we will introduce the Lorentz force, then we will study this expression in various conditions and significance of this Lorentz force, how this helps in doing many applications, when developing many applications from the understanding the charge particle to increasing the velocity. We will discuss here. In this lecture, a student will be able to learn calculation of Lorentz force, analysis of force on moving charges in the presence of electric and magnetic field simultaneously or one by one, and development of applications. Whenever we talk about force, we have many kinds of force. And in physics, actually, we know they have four kinds of force. And here we are talking about electromagnetic forces. Of course, other than this, we are having weak forces, strong forces, and gravitational forces. Now, whenever we are talking about electromagnetic forces, it means the forces due to electric and magnetic field and the forces on charged particles. The orange forces are those forces which exerted on a charged particle when the charged particle is moving with a velocity of v through electric field E and magnetic field B. We have discussed in the previous classes, if the charged particle is not moving, then there exists only electric field. The electric field exists and it has may create some field of the charged particle. But when the charged particle is moving, in electric field, then we have discussed that the electric field may change their path or may change their direction. But that change is only a particular direction. But magnetic field presence gives a lot of deviation in the path of the charged particles, which was given by Lorentz. So, whenever we talk about Lorentz force, we must know this is the force exerted on a charged particle. This is the force experienced by a charged particle when the charged particle is moving under the field, under the effect of electric and magnetic field both. Yes, we can also check here if the charge q is there, and we are applying, the charge is moving in with the velocity v, and we are applying b in any direction, then q v cross b is perpendicular to the both cross product, both perpendicular to direction of velocity and magnetic field. Actually, the first contribution term is contributed by electric field QE. This is the electric contribution. The second term is due to magnetic field. This has the direction perpendicular to both velocity and magnetic field. Interestingly, whenever we keep the charge particle, moving charge particle in the presence of electric and magnetic field, both field gives their effect individually. The first term is due to electric field, second term due to magnetic field. The magnetic force is proportional to Q and to the magnitude of cross product of V cross V. In terms of angle, if suppose there is an angle between V and B, the magnitude of the force is equal to QVB sin phi. It's a mathematical expression. We know this. A cross B is equal to AB sin theta. So by using it, you can calculate. An interesting result of the Lorentz force is the motion of charged particle in uniform electric field. Whenever charged particle moving in uniform magnetic field, it rotates. If your velocity of the particle is perpendicular to B, then you can calculate from QBB sin theta. The angle is 90. An angle will give you sin 90 is 1. So if your V is perpendicular to B, then you will we have QV. The particle will follow a circular trajectory and the radius will be equal to R is equal to MQVB. But if the angle is less than 90, the particle orbit will be a helix and axial parallel to the field lines. So try to learn this again. What happens if the phi is 0? There will be no magnetic field on the particle, which will continue to move undeflected if phi is 0. So we have to learn this and remember this theta. Whenever a particle is moving in magnetic field, three directions are possible. Either it is perpendicular to magnetic field, or it is parallel to magnetic field, or any angle between that. If it is perpendicular to magnetic field, it will rotate, it will move in the circular direction, that is, our trajectory will be circular. But if the angle is less than 90, it will orbit like a helix parallel to field lines. The charged particle accelerate like cyclotron, make use of fact that the particles move in circular orbit when B and B are at right angle. For each revolution, a carefully timed electric field gives particles additional energy, kinetic energy, which means that they may travel in increasingly large orbit. Actually, particle accelerator use this principle to increase the velocity of the charged particles. In the particle accelerator, we move the particle in electric and magnetic field. Magnetic field gives a lot of effect in moving the particle in circular direction. When the particle has acquired the desired energy, the required velocity, then we extract this particle from this accelerator. Many applications have been developed for studying. Actually, the lorentz force is very useful in developing the accelerators, developing a device which can increase the velocity of the particle. The magnetic phase force on a moving charge reveals the sign of the charge carrier in a conductor. The current flowing from right to left in a conductor can be result of positive charge carrier moving from right to left or negative charge carrier moving from left to right or some combination. Interestingly, the magnetic force can also give the idea of charge carrier. Yes, we have used this idea to obtain the presence of charge carrier, to get the idea of presence of charge carrier. As it is shown here, every time we can get the idea of charge carrier using right hand rule direction. Now, if you are having a conductor and you are trying to calculate current, then it can be done. By using these laws. Suppose current is flowing from right to left in a conductor. If the current is moving from right to left and the positive charge carrier is moving from right to left or negative charge moving from left to right, we know this and can be studied further. This behavior was used to calculate the type of charge carrier in semiconductors. I think all of you have the idea of semiconductor. In semiconductor, there is a issue of charge carriers. As far as whether you are having the charge carrier electron or hole. In the case of conductor, we always talk in terms of electrons. But in the case of semiconductors, we have two types of charge carriers, electrons and holes, absence of electrons. So there we can study when the current is conductor is placed in magnetic field B perpendicular to the current, the magnetic force on both type of charge carrier is in the same direction. This force gives rise to a small potential difference in the third direction that is called Hall effect. Hall effect was first discovered by Edwin H. Hall. This result when an electric field is aligned with the direction of magnetic force. So this shows the significance of Lorentz force. With the help of Lorentz force, we have developed the law. It is called Hall effect. Hall effect is one of the most important effects in semiconductors to calculate the charge carrier, to understand the behavior of charge carrier. This Hall effect shows that the electron dominate the conduction of electricity in copper. In zinc, however, the conduction is dominated by the motion of positive charge carrier. Electrons in zinc that are excited from valence band leaves hole, which are vacancies and behave like positive charge carriers. The motion of these holes account for most of the conduction of electricity in zinc. So that is important. Which is dominant, which is not, can be calculated using this behavior. So if a wire with a current I is placed in an external field, how much force on the wire depends on orientation of the wire. Since a current represents a movement of charge in the wire, the Lorentz force acts on moving charges. We have discussed a lot in the previous slides the concept of Lorentz force. These, because these charges are bound to the conductor, the magnetic force on the moving charges transferred to the wire. So interestingly, point out this, the charge particles, you are applying field on the charge particles and now the charge particles are bound to the conductor. Since the charge particles are bound to the conductor, the magnetic fields on the moving charge now transfer to the wire, to the conductor. The force on small length dl of the wire depends on orientation of the wire with respect to field. The magnitude of force is given by I dlb sin phi. Here I is the current, that is moving in the wire. B is the magnetic field, and dl is, we have taken small area, a small length of the wire dl. Actually here the magnetic Lorentz force is used and modified and updated for current. In current, the Lorentz force is IDL, B sin phi. Phi is the angle between magnetic field and the small wire element. If there is no force, when the phi is either phi 0 or 180, it means if the current is moving along the direction of magnetic field, then there will be no force. The force exists maximum when both are in perpendicular. And the force can be written as this: dF is equal to I dl cross B. Yes, we have moved towards current. We have started with charges. Now we have moved towards current. Moving charges will give you current, and in if we are having current, then this law will be modified like this. This is actually the second part, second component of Lorentz force. Here we have shown two examples, in fact, applications of Lorentz force. In the first, we have shown that the particle is moving and in a particular direction with a velocity v, and finally entering here in magnetic field from here. Here the magnetic field is given by dot. I think all of you may be aware of this word dot. We can represent magnetic field in two ways. One is dot, I have shown here, and second is cross. When we are using dot, it means magnetic field is in outward direction. Suppose you are making a dot on the paper, then the magnetic field is coming out from the paper. And if we are using cross, it means magnetic field inside the paper. In our case, we have taken dot. Dot means magnetic field outside the paper. So magnetic field is in outside the paper, and if we use right hand rule and we stretch the right hand palm, then the finger will give you the idea of direction of particles, then your particle will move either in above direction or in below direction using right hand rule. In this case, it may move in upward direction if the charge is less than zero. If the charge is more than zero, then it will move in downward direction. We use this property to separate out different charges. Sometimes we use this property in mass spectrograph to separate different charges. This can be done by velocity selector chamber. So this is one application we can use. In another application, a beam of electrons moving in a circle. This is due to the presence of magnetic field. If we move the beam of electron in a circle, in the figure we have shown using a purple light which is emitted along the electron path. Here the light shows the electrons are colliding with gas. We have passed these electrons through a gas molecules. So the electrons are moving in circular direction due to magnetic field. We have applied magnetic field perpendicular to it. So here in this slide we have shown two applications. One is separation of charges using magnetic field, and second one is motion of electrons in a circle. As we already discussed in the previous class, this motion of electrons can also be used to accelerate the velocity of the electrons. Here are certain applications of Lorentz force. We use Lorentz force in many devices like cyclotrons or other path particle accelerators. Cyclotron is one of the best application where we use the Lorentz force, and another applications are mass spectrophotometers to separate the different masses, isotopes. It can also be used in velocity filters if you want to separate a particular velocity. Normally, whenever we create the charge particles, the charge particles are of different velocities. So it can be used to get charge particle of particular velocity only. Magnetrons, Lorentz force velocimetry, and so these are the applications, and in its manifestation as the Lorentz force on electric in a conductor, this force occur in many devices like electric motors, rail guns, linear motors, loudspeakers, Magnetoplasmatic thrusters, electric generators, homopolar generators, alternators. So many electric applications we use this law. We have discussed this that this law is very useful for electric and magnetic field if we are using anywhere. And this law can be used to guide the charge particle stream. Thank you. We have discussed what is Lorentz force, what is the application of this force, what is the significance, how the direction can be calculated in these two lectures. Thank you.